Welcome, BS Agri first year, to our second lesson in organic chemistry. Today we are going to discuss about the classes of organic compounds. And the last meeting we talked about carbon as an important element in the formation of organic compounds. Carbon can form more compounds than any other element due to its ability to form single, double, and triple carbon-to-carbon bonds, and also link up with each other in chains and in ring structures. Classes of organic compounds can be distinguished according to functional groups they contain. A functional group is a group of atoms that is largely responsible for the chemical behavior of the parent molecule. Different molecules containing the same kind of functional group or groups undergo similar chemical reactions. Thus, by learning the characteristic properties of a few functional groups, we can study and understand the properties of many organic compounds. All organic compounds are derived from a group of compounds known as hydrocarbons, because they are made up of only hydrogen and carbon. On the basis of structure, hydrocarbons are divided into two main classes: aliphatic and aromatic. Aliphatic hydrocarbons do not contain the benzene group or the benzene ring, while aromatic hydrocarbons contain one or more benzene rings. So this topic, we will discuss it deeply. We will be having a deep discussion, a thorough discussion about this later on. So we will be having a short review of what we learned during our previous lesson. So we learned that covalent compounds are formed by the sharing of valence electron of two or more nonmetal atoms, and that is what we call covalent bonding. So the key word here is the sharing of valence electron. Organic compounds are covalent compounds because they are formed by the sharing of valence electron between two or more nonmetal atoms. How did it happen? Again, we will go back to the octet rule. It is also called the rule of 8 or the stability rule, which states that an atom other than or except hydrogen tends to form bonds until it is surrounded by 8 valence electrons. So for an element except hydrogen, which gains stability by having 2 electrons, all other atoms will form bonds or will share with other atoms to form 8 valence electron in order to attain stability. Atom is stable if it has 2 electrons in the first energy level and 8 outermost electron. And that outermost electron is called the valence electron. The sharing of valence electrons between two or more non-metal atoms is called covalent bonding. We also discussed about the Lewis dot symbol, which consists of the symbol of an element and one dot for its valence electron in an atom of the element. So the figure shows the elements from group 1A up to 8A and the corresponding Lewis dot symbol of the element. So you can see that the hydrogen that belongs to group 1 has 1 dot, meaning it has 1 valence electron, while the carbon in group 4A has 4 dots or 4 valence electrons. Let us now examine the ability of carbon to form different bonds with another carbon atom or with hydrogen atom. Here you can see that one atom of carbon actually shares with one valence electron of the 4 hydrogen atoms. So, by sharing with this one valence electron of carbon, or rather hydrogen, the carbon or each hydrogen that shared with the valence electron of carbon becomes stable by using 2 valence electron, while the carbon also attains stability by sharing with the valence electron of each 4 hydrogen atom. Notice that carbon formed 4 single bonds with 4 atoms of hydrogen. Each hydrogen becomes stable because of the shared electrons of 2. For hydrogen, the minimum requirements to attain stability is to have an electron of 2. For the atom of carbon, sharing with one valence electron of each hydrogen atom, carbon has now a total of 8 valence electrons, making it stable. That is according to the octet rule. Each bond between carbon and hydrogen represents the shared electrons. A single bond represents 2 shared valence electrons between carbon and hydrogen. Aside from bonding with hydrogen atom, carbon can also form bond with other carbon atom. In this illustration, you can see that the carbon bonded to hydrogen can also bond with other carbon atom, either in a single, in a double, or in a triple bond. Here you can notice that the bond that exists between the 2 carbon atom is double bond. Each hydrogen atom becomes stable by sharing with 2 valence electron of carbon. Each carbon atom becomes stable by sharing a total of 8 valence electron. So you can notice that carbon formed double bond with another carbon atom to complete the 8 valence electron. A carbon may also form triple bond with another carbon. In this case, you can see that the carbon atom bonded to hydrogen on the opposite of the molecule, but between carbon and another carbon, we can see the triple bond. Okay, so before moving on to the types of aliphatic hydrocarbons, let us be familiar with the different chemical formula. Because in our subject, we will be bombarded with so many chemical formula or molecular formula. So what is chemical formula? It is a way of presenting information about the chemical proportions of atoms that constitute a particular chemical compound or molecule, using element symbol and the subscript number at the lower right side of the element symbol that represents the number of atoms. Example, water has a chemical formula or molecular formula of H2O. H stands for the hydrogen atom and O stands for the oxygen atom. The small 2 or the subscript 2 indicates the number of atoms of the hydrogen. Meaning, water is composed of 2 atoms of hydrogen and 1 atom of oxygen. Another is, the chemical formula of carbon dioxide is CO2, meaning carbon dioxide is composed of 1 atom of carbon and 2 atoms of oxygen. The structural formula. It shows how atoms are bonded to one another in a molecule. So water with a chemical formula of H2O has a structural formula of H single bond to O and another hydrogen or H single bonded to oxygen. Carbon dioxide has structural formula of oxygen bonded or double bond with carbon. For now, we will just focus on these two formula, but later in our discussion, we will come across the other types of formulas. Classification of hydrocarbons. You can see the hydrocarbons are classified into aliphatic and the aromatic. Under aliphatic hydrocarbons, we have the alkanes, the cycloalkanes, the alkenes, and the alkynes. Alkanes. Alkanes have the general formula of CnH2n plus 2, where n is equal to 1, 2, and so on. The essential characteristics of alkane hydrocarbon molecules is that only single bonds are present. So alkanes has the characteristics of having a single bonds between each carbon atom in a molecule. The alkanes are known as saturated hydrocarbons because they contain the maximum number of hydrogen atoms that can bond with the number of carbon atoms present. The simplest alkane, that is with N is equal to 1 or with only one carbon, is methane, CH4, the chemical formula. So we have one carbon and 4 hydrogen atoms. That's the simplest alkane, called methane, which is a natural product of the anaerobic bacterial decomposition of vegetable matter underwater. Because it was first collected in marshes, methane became known as marsh gas. A rather improbable but proven source of methane is termites. When these voracious insects consume wood, the microorganisms that inhabit their digestive system break down cellulose, the major component of wood, into methane, carbon dioxide, and other compounds. The first 10 straight-chain alkanes. Here you can see we have 4 columns. First column is the name, then the chemical formula. We have also the structural formula and the number of carbons present. So the first type of alkane is the methane. Methane with a chemical formula of CH4, 1 carbon and 4 hydrogens. You can see the structural formula. Carbon as the center, carbon at the center, the central atom, bonded to 4 hydrogen atoms. So the number of carbon atom is 1. The next is the ethane. The ethane with chemical formula C2H6 is composed of 2 carbon atoms and 6 hydrogen atoms. The number of carbon is 2. The third one is the profane. The profane with chemical formula C3H8. 3 carbon atoms and H or the hydrogen 8 atoms. The number of carbon atom is 3. Next is butane. Butane has a chemical formula of C4H10. The number of carbon is 4. Pentane, C5H12. The number of carbon is 5. Hexane, C6H14. That's the chemical formula. And the number of carbon is 6. Heptane, C7H16. The number of carbon is 7. Octane, C8H18. The number of carbon is 8. Nonane, C9H20. Number of carbon atoms, 9. And decane, C10H22. The number of carbon is 10. So the first 4 alkanes, the methane, the ethane, the profane, and butane, have non-systematic names. Alkanes containing 5 to 10 carbons use the following prefixes and suffix. Ane, So as you can see in the table, the number of carbons in the chemical formula and the prefix and the suffix "ane" and the name. So we can see the CH4 has a carbon of 1, the prefix meth plus the suffix "ane." So the name is methane. C2H6, number of carbon is 2. The prefix is eth plus ane. The name is ethane. C3H8, the carbon is 3. The prefix is prof plus the suffix ane. The name is profane. C4H10, number of carbon is 4. The prefix but plus the suffix ane, the name is butane. So from alkanes with 5 to 10 carbons, we will be using the Greek prefixes. So we have for the carbon or the C5H12 with a carbon, number of carbon is 5, we use penta, meaning 5, plus the suffix ane, so we have pentane. An alkane with 6 carbon, hexa, plus the suffix ane, we have hexane. 7, the alkane with 7 carbons, hepta, plus the suffix ane, heptane. C8H18 with 8 carbons, octa, and the name is octane. C9H20, the carbon is 9 and the prefix nonane or nona plus the suffix ane, that's nonane. And C10H22, 10 number of carbons, that is deca, plus the suffix ane, the name is decane. The simplest alkane is methane. The structure of ethane and profane are straightforward, for there is only one way to join the carbon atoms in these molecules. Butane, C4H10, however, has 2 possible bonding schemes. Bonding schemes resulting in structural isomers. Molecules having the same molecular formula but different structures. There are 2 structural isomers for butane. Number 1 is the N-butane. N stands for normal. So the N-butane looks like this. So we have 4 carbon atoms bonded with each other and bonded to the 10 hydrogen atoms. N-butane is a straight chain alkane because the carbon atoms are joined along one line. Another type is the isobutane. It's a branched chain alkane. In a branched chain alkane like isobutane, 1 or more carbon atoms are bonded to at least 3 carbon atoms. So you can see here that the carbon atom, one of the carbon atom is actually bonded to the other or to the chain of a carbon atom. So let us compare now the structure of the N-butane and isobutane. So can you see the difference between the two, the N-butane and the isobutane? So they have the same number of carbon atoms and hydrogen atoms, right? But what can you see, or what difference can you see in these two? The alkyl group. An alkane less 1 hydrogen atom is an alkyl group. For example, when hydrogen atom is removed from methane, CH4, we are left with CH3, which is called a methyl group. Similarly, removing a hydrogen atoms from ethane, that is C2H6, gives an ethyl group or C2H5. The names of alkyl groups. Alkyl groups are named by replacing the suffix "ane" with YL. Therefore, the methane CH4, when we remove 1 hydrogen, it will have 3 hydrogen, and the name is methyl. The ethane, C2H6. When we remove 1 hydrogen, it becomes C2H5, and the name is ethyl. These are the common alkyl groups. You can see on the table, we can see the methyl, the ethyl, the N-propyl, the butyl, isopropyl, and T-butyl. Those are the common alkyl groups. The substituent group is an atom or group of atoms which replaces one or more hydrogen atoms on the parent chain of the hydrocarbon. So aside from the alkyl group, we have also the substituent group. These are the group of atoms other than hydrogen that can replace any of the hydrogen in the molecule, in the organic compound. So we have the names of the common substituent group. We have NH2, that's amino, F, that's fluoro, Cl, that's chloro, Br, bromo, I, iodo, NO2, that's nitro, and CH, double bond to CH2, that is vinyl. Condensed structural formula. So the condensed structural formula show the order of atoms like a structural formula, but are written in a single line to save space and make it more convenient and faster to write out. So, because writing structural formula requires more space, because we are showing all the bond line that exists between each carbon atom and hydrogen atoms, we will use condensed structural formula. Here you can see the structural formula of the heptane having 7 carbons, 1, 2, 3, 4, 5, 6, 7, bonded to hydrogen atoms. So you can see in condensed formula, we just copy and we will not show anymore the bond that exists between each hydrogen atom. Rather, what we are going to retain is the bond that exists between each carbon atom. So for the first part of the structural formula of heptane, we can see carbon bonded to 3 hydrogen. So we write that as CH3. And that carbon is bonded to another carbon, which is bonded also to 2 hydrogen atom. That is CH2. So continue writing it. We have another CH2, 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 and CH3. That is the condensed structural formula of heptane. Remember, in a condensed structural formula, we will no longer show the bond that exists between the carbon and hydrogen atom to save time and to write it more convenient for us and more faster to write it out. And the alkane nomenclature naming. So when we say nomenclature, that's naming. This is a systematic way of giving names to our organic compounds. This is actually based on the recommendations of international organization called Union of Pure and Applied Chemistry, or the IUPAC. So rules in naming alkane. So we will find the longest continuous carbon chain. The longest continuous carbon chain is also called the parent chain. So we will count the longest. We will count the longest continuous chain of carbon. So in this example, how many carbons do we have? How many carbon, a continuous chain of carbon do we have? So we have 1, 2, 3, 4, 5, 6, 7. So 7. So that is heptane. The alkane, the name of the alkane is heptane because we have 7 carbons. So the parent name of the hydrocarbon is that given to the longest continuous chain of carbon atoms in a molecule. Again, we count the number of carbons, continuous chain of carbon, continuous and straight chain. No? Take note, it's a continuous and straight chain of carbon atoms. So here, we put a number, or we numbered the carbon atoms in our continuous chain. 1, 2, 3, 4 carbon, 5 carbon, 6 carbon, 7 carbon. So we have 7 carbons in this molecule. So therefore, the name of the parent name or the parent chain is heptane, because there are 7 carbon atoms in the longest chain. Now, notice that in carbon 4, there is an attached alkyl group. And the name of that alkyl group is the methyl. Methyl is an alkyl group because it is actually minus 1 hydrogen from the methane. So this is ethyl with CH3 formula attached to carbon 4. So the name of the alkane is, we will first indicate the location of the alkyl group. The alkyl group's methyl is attached to the carbon 4. So we will indicate the location of the alkyl group. The alkyl group is attached to carbon 4. So we have 4. Then we have the hyphen. What alkyl group is being attached to the carbon 4? Of course, the methyl. And the name of the parent chain, the longest continuous chain of carbon, is heptane. So 4 here stands for the number of carbon where alkyl group attached, or the location of the alkyl group. The methyl is the alkyl group attached to the carbon number 4. Heptane is the name of the parent chain, or the longest chain of carbon. So the name of this is 4-methylheptane. Note, the branch name alkyl group methyl and the parent name heptane are written as a single word, lowercase, and a hyphen follows the number. When there is more than one alkyl group of the same kind present, we use the prefix such as di, meaning 2, tri, 3, tetra, 4, penta, 5, hexa, 6, hepta, 7, octa, 8, nona, 9, and 10, deca. In this example, you can see that there are 2 alkyl group attached to the parent molecule. There are 2. And what are those? We have 2-methyl. We have 2-methyl attached to the carbon number 2 and carbon number 3. So the parent chain consists of 6 carbons. So the name of the parent chain is hexane. The 2 alkyl group of the same type attached to it, to the carbon 2 and carbon 3, is CH3 or methyl. Since we have 2-methyl attached to our parent chain, we will use the prefix di to note or to denote the number of the methyl group attached. So the name of the compound is 2,3-dimethylhexane. So we have more examples here. You can see in the illustration, the parent chain has 6 carbons, so the parent name is hexane. We have 2 alkyl group attached to the carbon 3. They are the same alkyl group, and that is the methyl. So the name is 3,3 hyphen di, because they are 2, methyl, because the alkyl group attached are methyl, and the parent is hexane. So the name is 3,3-dimethylhexane. Example below, we have how many carbons? How many chain of carbon do we have? We have 1, 2, 3, 4, 5, 6. So 6 also. We have 6 longest chain, continuous chain of carbon. So that's hexane. We have alkyl group attached to carbon number 3. There are 2. So the alkyl group is ethyl. The ethyl. And so the name is 3,3-diethylhexane. So another example is 3,3-dipropylhexane. The name of the parent is hexane because we have 6 carbon chain. And there are alkyl group attached to the carbon number 3, and that is the propyl. We have 2. So the name is 3,3-dipropylhexane. We have also, in the example below, the parent chain is pentane because we have 5 carbon chain or 5 carbon continuous chain of carbon. So attached to the second carbon and on the third carbon are the methyl group. So indicate the location of the alkyl groups attached. We have in the carbon number 2, and we have also in the carbon number 3. And since they are of the same type, which is methyl, so the name is 2,3,3-trimethyl pentane. Okay? Trimethyl pentane. Because the alkyl group is methyl. For the next example, we have 3-methyl attached to the second, the third, and the fourth carbon. The parent name is pentane. So the name is, since they are 3, we indicate the location of the alkyl group where they are attached. So we have carbon 2, carbon 3, and carbon 4. So 2, 3, 4, since they are 3, we have trimethyl pentane. The next example is the parent chain is butane. 1, 2, 3, 4. We have 4 straight chain of carbon atoms. So that's butane. And we have alkyl groups, the same alkyl groups, methyl. So we have the location is from, on the carbon 2, carbon 3, and carbon 4. So we have 2, 3, 4, 4, tetra. Tetra because we have 4 methyl group. Tetramethyl-butane. When there are 2 or more different alkyl groups present, the names of the groups are listed alphabetically. For example, in this example, we have the parent chain heptane. But we have alkyl group of different types attached to different location of carbon. So the first one you can see in the third carbon, attached to it is the methyl. And on the fourth carbon, attached to it is the ethyl, the C2H5. So since they are of different type of alkyl group, we will alphabetize. We will arrange them alphabetically. So, ethyl, letter E, is or should be the first. And the methyl, or the M, will be the last in the alphabet. So the first in the alphabet is the E, and the M will be the last. Therefore, the name is 4-ethyl 3-methyl heptane. On the next example, we have 3-methyl and 4-propyl heptane. What happened is the alkyl group attached to the carbon 3 is the methyl, while the alkyl group attached to carbon 4 is the propyl. So M in the alphabet and P in the alphabet, the one we will mention first is M, because M is ahead of P in the alphabet. So the name is 3-methyl 4-propyl heptane. Of course, alkanes can have many different types of substituents. So aside from the alkyl group, we have also the substituent group. You can see in the table the names of common substituent groups. We have the NH2, that's the amino. The F is the fluoro. The Cl is the chloro. Bromo, Br, iodo. NO2, nitro. And CH, double bond to CH2, that's vinyl. In this example, you can see that we have the parent chain butane, because we have 4 longest chain of carbon atoms. Carbon atoms. We have also the substituent groups, 2 substituent group. The one is Br, or the bromo, and the NO2 is the amino. The bromo is attached to the carbon 2, and the nitro is attached to the carbon 3. Now, looking back at the alphabetical order, bromo, or B, is ahead of the nitro, which is N. So in the alphabet, letter B is ahead of letter N. So therefore, the name is 2-bromo, because the bromo is attached to the carbon 2, and 3-nitro-butane. Another example is 1-bromo, 3-nitro-butane. The bromo is attached to the carbon 1, that's why we have 1-bromo, and the nitro is attached to the carbon 3, that's why we have 3-nitro-butane. Another example is we have 3-bromo, 4-chloro, 2-fluoropentane. So let us see what happened. So we have 3 substituent groups attached to our parent chain, pentane. And following the alphabetical order, we have bromo should be the first, then followed by the chloro, which is letter C, and the last is the fluoro, which is the F. So the locations are the following. So bromo is located or attached to the carbon 3, that's why we have 3-bromo. Chloro is attached to the carbon 4, that's why we have 4-chloro, and fluoro is attached to the carbon 2. That's why we have 2-fluoropentane. And we have 3,3-diaminohexane. Why di? Because we have two substituent groups of the same kind. That's why we will be using the prefix di. And this amino substituent group amino are attached to the carbon 3. That's why we have 3,3 diaminohexane. So, that is how we give names to our alkanes. I hope that you can review the video lesson. You can watch it repeatedly so you can understand how we are going to give names to our alkanes. I will give you 1 week time to watch the video repeatedly and to post it and to jot down notes for you to fully understand the way or the method or the steps in naming the alkanes. It's quite complicated. In the first, especially since we are not used with these compounds, but hopefully through your persistence and through your perseverance, you can understand the way or the method or the steps in naming these alkanes. So next meeting, I will be posting in the Google Classroom your second chapter test about naming alkanes and about the second lesson that we discussed today. Thank you very much for your time. Thank you very much for watching our lesson. And see you next Monday for another lesson in organic chemistry. God bless everyone and good day.